Thank you. I'm Calton, and this work was part of a thesis work of Lei Yu, the first author. He graduated and joined IBM, so instead of coming here to give a job talk, he decided to let us advertise on his behalf. So he's jointly advised by Professor Lin Liu and myself, and we still have two good students. So if you're recruiting, Emery and Stacy are very good students. The paper is about deep learning with differential privacy, and as you have seen from the previous speakers, this is a topic that has been a big challenge, and we have made some progress, so we do not certainly claim we have the final answer by far, but we do have interesting results in terms of privacy budget allocation and also privacy cost estimation, as well as calculation with the evaluation. So deep learning, of course, is kind of considered widely to be the next big hope in terms of smart applications, and I thank the first speaker, Om, for giving a very nice introduction of differential privacy, so we don't have to repeat that, but of course you are probably familiar with deep learning as well. So you probably know that deep learning can achieve higher accuracy and performance compared to normal machine learning algorithms that have been presented earlier here. But deep learning has a dependence on very large amount of training data. So it achieves higher performance because it has better input, so to speak. And it has also a better capture of the information in the input. So that causes problems. And, but there are certain applications that we really need this higher performance. So for healthcare applications, cancer was mentioned earlier. We also use cancer dataset. You can imagine that false positives are not going to be a very good, very good answer. So we need a high performance, and deep learning provides that hope. And we have then now privacy leakage problems. So I think Om mentioned membership inference attacks, and also there's a model inversion attack. And then there are other ways, actually imaginative ways of misleading both the models as well as the results. So we are going to talk a little bit about this. And so what happens is we have a training data set. Of course, we cannot reveal that as part of the privacy protection. And then the hope is that with deep learning, we have very sophisticated neural networks, and we go through a lot of training, and we added the stochastic gradient descent curve here. You will see this curve a little bit later. But the idea is that through optimization, then we can minimize error, and then we have a model that we could potentially publish and hopefully not reveal the actual delicate parts, the privacy that we're trying to preserve. So the hope is that the model then can be shared and then published. So the problem is that deep learning captures the information from the input. And by doing that, the models actually contain a lot of information about the input. So intuitively, what's happening here is that we have a lot of iterations, we have a lot of optimization, and the models actually reflect very interesting details about the input. And that's part of the reason why the membership attacks and the model inversion attacks are actually quite powerful in this case, because the information is actually captured in the models. So, so now the problem is we have a deep learning, and we would like to use it, but it is in a way working against itself from privacy point of view, because the more information that you capture in the models, the more risk that you have in revealing those when you publish the models. So what we have here is that we have a model publishing, and we would like to leverage some of the work in terms of the budget allocation, the privacy budget allocation, and also the privacy cost estimation. So maybe we can fine-tune those two and then achieve a better balance in terms of how to preserve differential privacy here. So I will just flash this slide. Thank Om for having explained the differential privacy. And I hope that you have come in time to have caught his explanation. So for those of you who came a little bit late, I apologize. But there is this definition, and the idea of differential privacy at a very high level is this trade-off between utility and privacy. So you try to balance the best of preserving utility of the data while perturbing just enough so you can also preserve privacy at the same time. So one of the things that may or may not have mentioned explicitly, this composition theorem, that there is a very nice property in differential privacy that you can actually combine different algorithms. And if the algorithms are combined carefully, in this case, each one of them executed sequentially over the entire input data, then you can actually add up the privacy budget allocation there. And in our case, we do the other way. We actually use this fact and then decompose the privacy budget into the different parts of the algorithm that we're trying to run here. So the epsilon in this case can be decomposed into different smaller budgets. And then in case of multi-step machine learning, which is the case of deep learning, we actually decompose this privacy budget, allocate the sub-budget for each step. So there are different ways of allocating this budget, and we're going to show that actually, depending on the way you allocate the budget, you get different results. So even though maybe theoretically they look very similar, in practice there are differences in how you do this. And in particularly, we are going to show you some examples where this makes big difference, and other times when they may or may not make that big a difference. So stochastic gradient descent has this iteration. So we have two parts of the iteration, but just at a very high level, we go through the entire data set in what we call the epochs, and then each data set can be decomposed into smaller mini batches, and then we can have iterations over those mini batches within each epoch. And the idea is that you can, for example, execute the mini batches in parallel over GPUs, speed up the process. And the idea is that if we are careful in how we divide things and how we divide the privacy budget, then we can actually achieve better results. So summarizing the technical challenge here, there are two parts. So the first part is a privacy budget allocation, and the second part is the privacy cost accounting. So the budget allocation in this case will be the way we divide, so Ohm divided into two parts, and in this case we have deep learning, we have many different steps, so we divide actually the budget over those steps. And the cost accounting in this case also is important because we need to make sure that as we add up each step, we do not exceed the budget. And so random sampling and random shuffling are the two popular methods for doing this. And even though mathematically they are very similar, have similar statistical properties, for the case of privacy preservation, actually they have some differences in this case. So finally, we are at the point where we can summarize the contribution of the paper. So there are two parts of this. One is the budget allocation, and the other one is the cost analysis, the privacy cost analysis in terms of random sampling versus random shuffling. And then there are different data batching, mini-batch allocations that actually also make a difference. So in terms of mini-batch, let me just, I see that I'm actually running short on time. So I will just be very brief about this. So random sampling, in this case, has replacement, as you can imagine. And random shuffling, in this case, allocates the data set into smaller parts, smaller subsets, without replacement. And turns out that random shuffling has good properties in terms of how we divide into parallel execution unit. So they are more efficient in execution. And in software packages like TensorFlow, PyTorch, that's quite often the default way to do this. So for data mini-batching, turns out that random sampling actually has better properties. So random shuffling is more efficient execution, but because it is known that we actually choose each point exactly once, so you can see that random shuffling actually has higher cost and it requires a higher budget in terms of privacy preservation. So those are the curves that we show that in the paper, that for random shuffling, you actually need to be more careful. So for random shuffling, turns out that there is a concentrated differential privacy method called a zero concentrated differential privacy that we can use to calculate the budget as well as the cost. So in this particular case, I have to go quickly, but turns out that we found that because of the shuffling actually uses each data point exactly once, there is a good thing about this in terms of the zero concentrated differential privacy. So actually, we can show that it is actually preserving better, a tighter bound in this case. And for the random sampling, there is also interesting observation that it actually preserves the privacy budget in a way, at least for the initial segment in terms of the alpha parameter here. And this is not previously clearly identified. So this is one explanation of why random sampling can achieve tighter privacy preservation compared to the shuffling. So one thing that I want to briefly mention here is that we actually looked into the budget allocation issue, and we found that smarter budget allocation actually can improve the algorithm in this case. And you will see that the graph here kind of resemble the SGD graphs. So we basically said that in stochastic gradual descent, what you have is a higher learning rate at the beginning and a slower learning rate a little later. So what we do is to allocate more privacy budget at the beginning and lower, smaller privacy budget later on as the learning rate slows down. So we tried four different alternatives in this case, and in this particular case, we show that also that the validation data set can be the public part of the validation to save on the privacy budget. And so we have used this to evaluate the four different decaying functions in terms of how we reduce the privacy budget allocation over time. And this we show that actually they do better compared to the constant allocation. If you divide everything the same, then you will have a lower performance accuracy, for example, compared to all of the variable dynamic allocation algorithms there. Now, the difference between the variations of dynamic allocation is not as big as we thought. We thought that having different ways of allocating it would make a bigger difference, but the difference was less than we thought. So this is definitely a question in terms of allocating smartly the budget. The privacy budget is definitely a question that is, in our mind, more intricate question. It's not as easy, as obvious as we thought originally. So in this particular case, we show that you have random shuffling having higher budget, and then the random sampling, as well as different ways of equivalent of to random sampling in terms of how to do the budget allocation, you can achieve better performance in this case. So the summary of the talk, and I apologize that I kind of run over some of the technical issues there. So we have done the privacy loss analysis in terms of both the budgeting and also the cost analysis. And in this case, we show that it's not as obvious as we thought, and it has several components of the problem, and some of the things have higher impact than we thought, and the other parameters have a lower impact than we thought. So the privacy budget allocation, in this case, we know that it makes a difference, and the variable, the dynamic allocation, does improve the final result. And the source code is published on GitHub. And we have a revised version of the paper with improved language on archive. So if you want to look further, and we really welcome your comment and further discussions, please take a look at the archive version. Thank you.
Okay, do we have any questions? So I got one question. When you were presenting these comparisons with various schedules, you didn't show us what the non-differential private version was. So it's kind of hard to tell what the scale is. How much do you lose by being differential private at all in terms of accuracy?
Oh, okay. That is a really good question, and Lei actually mentioned that could be, but that is one question that he had cautioned me to defer to him. Yes, of course, as our previous two speakers have shown, that it's important to compare the differential private versions with non-differential private versions in terms of utility, for example. But in this particular case, we are assuming that we are comparing different differential privacies. So yes, you're absolutely right in terms of if we compare with the known differential private versions, that would be also another part of an interesting comparison.
And speaking of utility, you've shown us that the shuffling version of the sampling, based on shuffling, is much worse in terms of the privacy budget. But how much better is it in terms of sort of the practice of deep learning? Why do people use it? Is it as easy as let's switch to random sampling and forget about shuffling and we'll make the right decision, or is it more nuanced than that?
Thank you for asking that question. That's actually a part that I skipped over. So what happens is if I may, it's already off. So I'm sorry. So the question was whether in practical terms there are differences between shuffling, and sampling is more expensive if you were to calculate it using the definition how it is supposed to be calculated. So turns out that shuffling has much easier way of calculating. And part of the reason is because of the, for example, one explanation for that is a zero CDP way of calculating the budget. And for the random sampling, actually, there is no way, no proof, no theorem that shows a particular bound. So what we have actually in the archive version of the paper is an empirical bound, and we have an analytic expression to calculate it that is easy to calculate and efficient to calculate. But this is actually one example of a research challenge for us to look into in terms of how we actually can prove tighter bounds for the random sampling case.
Okay, thank you. Any final questions?
Thank you for the talk. So you mentioned that moments accountant doesn't apply to reshuffling, and ZCDP currently doesn't apply to sampling. So is it fair to say that if you're doing sampling, you should go for moments accountant, and if you're doing reshuffling, you should go for?
That is actually a technical question that I know answer of. So thank you. Yes, that is a question for people who are doing differential privacy. And yes, if you're doing moment accounting, you need to choose specifically random sampling, because what we show is there's a difference. So if you, by default, used shuffling, your result may or may not be what you expected. Yes, thank you.
Thank you so much.
Mm-hmm.
All right, we might have time for one more quick question if anyone has it. Otherwise, oh yes.
To compute the privacy budget changes over time, I know of a method called privacy buckets that was published about a year ago that estimates sort of the privacy loss for each probability by drawing the privacy loss distribution and composing them. Have you tried this, and do you know how it how it performs compared to the moments accountant? And
Okay, I'm sorry, I only heard some of the words. I couldn't hear the entire sentence of, I would say, 1/3 of your question.
oh, sorry. So the privacy buckets method is sometimes used. It's a recent method to approximate privacy budget over time. And I was wondering how it was performing in relation to the moments accountant in the differentially private learning applications.
You said buckets?
Privacy buckets, yeah, that's the
Privacy
name
buckets.
of the...
Okay, so you can see that I'm not familiar with this. This is a question I would defer to Lei, and I would love to talk to you more about this and make sure that offline we have this question answered. Thank you.
Okay, let's thank Calton one more time.
Thank you. Thank you.